I decided to give my topic in 4 lectures, so we'll have 3 breaks. Each lecture is about 35 to 40 minutes long, and I can also remove some subjects if I notice that we all get too tired and want to go to the Galand beach. So this is about time parallel time integration methods, and the first part is shooting type methods, multiple shooting type methods. So this will occupy us for the first 35, 40 minutes. But before I want to start with this topic, I want to explain what this is, this time parallel time integration. So it's time-dependent problems. Here is an example. There is a heat equation. You see the derivative of u with respect to t equals a Laplacian of u plus some source function. An initial condition is given, and we're supposed to solve this problem over a certain time interval. Now, in general, to solve such a problem on a computer, you discretize the Laplacian like we've seen in Keith's talk, finite difference method, for example, in space. Then in time, you do a discretization like backward Euler, an implicit discretization. And then you do time stepping. So you start with your initial condition here, given a time t0 in all space. And then you do a time step forward to get an approximate solution at the next time step, t1. And once you know this approximation, you do a time step to get to the next time point, t2. And you advance like this. So you see, this process is completely sequential. You cannot calculate the solution here before you know what the solution here is, because it depends on this solution. There is a causality in this equation. This is a completely sequential process. This becomes even more clear if I take a simpler equation. Here is an ODE. u dt equals f of u, scalar ODE, just one unknown, initial condition given. Now I only have to discretize the time direction. Suppose I discretize by forward Euler. Forward Euler, so I get the new value is the old value plus delta t times f evaluated at the old value. So if I know u0, I can put it here and here, I get u1. Then this u1 I can put here, and I get u2, and so on. This is completely sequential. There is nothing that you can parallelize in this process, if you look at it like this. If the problem is linear, now I have a linear ODE, u prime equals au plus f. I do the same Euler discretization. Then I can write this as a system with all the unknowns at each time point, and I get a lower bidiagonal matrix. So from the first equation, I can determine u1, where the initial condition is here in the right-hand side. From the second equation, once I know u1, I can determine u2, and so on. This is completely sequential. It's a triangular matrix. So time parallel time integration are methods which allow to solve you this in parallel using many processors. And it doesn't seem possible if you look at the process because it's completely sequential. How can you possibly solve U100 if you don't know U99? Now, this has a long history, this subject area. It's about 50 years. And here is an overview of what I found. To make this presentation, I decided to search in the literature the papers that had a key new idea. And I will explain this key new idea for all the papers I found. This took about 2 years, and I didn't only do this for this presentation. I worked on this over the last about 2.5, 3 years. And what you see in this graph is time. There is a time axis. It's cutting apart here. There should be 2010, 2000, 1990. So you see time is advancing from 1960 to 2010 here. Then there is another axis here on top. In the middle it says large scale. And on the sides it says small scale. This means the methods that are described in these papers, if they're closer to the middle, they allow to use many processors to do this in parallel. And the methods to the boundary they only allow you to use a few multi-core architectures to do it in parallel. And then there are 4 colors on this. In 2 tracks, one track is here, the other track is here. This is direct methods. These don't iterate. They solve this problem over a long time interval without iteration. These are the black methods here. And then in this track here, there are iterative methods, 3 more colors. So you have 4 colors on this transparency, and these 4 colors correspond to the 4 lectures I will give. So there's going to be a lecture about the black methods, a lecture about the red methods, a lecture about the magenta methods, and a lecture about the blue methods here. Now I said there are 4 colors. It's not quite true. There is a 5th color. Did you identify the 5th color? The 5th color is review papers on this subject. There was a review paper by Gear. There is a book by Burridge. This is a book I read when I was a graduate student. It was a fairly recent book at that time. I didn't like it. Somehow there was no theorems, there was explanations, but no theorems. But it's a good overview of what was available then. And here's the review I wrote. And in this paper, you can download it from my webpage, you find most of what I explained today. So you can go and read of it, and it's explained like I explained it in the talk. So you should remember what I said when you read this review paper. So I start with the multiple shooting type methods. These are the magenta methods on this graph. And the first idea goes back to a paper by Nieuwergeld in 1964, which was not really an iterative method. It was a direct method, but the idea led to iterative methods here. And it was this paper by Lyons-Mede and Turinici which sparked a lot of activity in this field again. Before, people had worked on it, but a lot of activity was sparked by this method here. So I will explain now the key ideas of these 5 magenta papers in the next half hour. So the first was this Nieuwergeld paper, 1964. Nieuwergeld was to become a professor of mathematics in Zurich at ETH. During the time I was a student, but I never had a course of his. I don't know why it didn't happen. It just didn't happen. He was a postdoc in the US at that time. And he published a paper where he says, for the last 20 years, one has tried to speed up numerical computations mainly by providing ever faster computers. Today, as it appears that one is getting closer to the maximal speed of electronic components, emphasis is put on allowing operations to be performed in parallel. In the near future, much of numerical analysis will have to be recast in a more parallel form. That was in 1964. You have seen in transparencies during the CEMRACS school, this point has arrived, but 40 years later. You see on this graph what Nieuwergeld said today in 1964. It did happen only 40 years later, but 40 years later, we arrived at this time. So in this graph, you see time here that goes from 1985 to 2010. And here you see a log scale of powers of 10. And then you see the number of transistors that can be put on a chip, which is going up, is going up, is going up. There seems to be no bound. You can put more and more. But then all the other curves have a kink that comes in 2004, 40 years after the vision of Nieuwergeld. And you see, for example, the curve that says how many cores you put on a chip. It used to be 1 core. And suddenly, you have multi-core, 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 it's going up. Whereas the other curves flatten out. For example, the curve of the clock speed, suddenly it flattens out. You cannot go faster. It's a physical boundary. You just cannot go faster. So the only way to go faster now, as we heard this morning, is to go parallel. And so he, 50 years ago, thought about how we could do a parallel algorithm for a problem that somehow is not parallelizable. So that was the first idea. So here is his example. He takes an ODE, y prime equals f of y, with an initial condition. And he says, as an example, a method is proposed for parallelizing the numerical integration of an ordinary differential equation, which processed by all standard methods is entirely serial. Like I explained to you, There does not seem to be any parallelism in this. So he assumes he has an infinite number of processors, as many as you want. Just processors to waste. Is it possible to get this solution faster than just time stepping through? And here is his algorithm. The idea is as follows. It's an OD, so we have one quantity to calculate at each point. So the trajectory starts here, and he needs to know the solution along all these points. What he does first, he does a coarse approximation. He starts at this point, and he produces a coarse approximation, which is not going to be very close to the true solution. But this gives him an area where the solution should go through, approximately. Then he forms a cloud of points around this area, just some distribution of points of starting values. And he takes for each of those points a processor to calculate a very accurate trajectory. So here you see he's really burning processing power. He doesn't need any of these trajectories, really, because he doesn't know yet where it's going to go through exactly. But he calculates all these accurate trajectories, and then he does interpolation. Once he knows where this trajectory arrives, he interpolates among these points the point that is where the trajectory comes, and he also interpolates the accurate solutions to know where the point should go through here, and he continues like this. So all this interpolation is much cheaper than the accurate trajectory that he has to calculate, and so he can get the solution faster than if he had calculated sequentially an expensive trajectory. It's an amazing idea. There is a round-off error analysis. There is also truncation error analysis. It's not a very useful algorithm like this, but it's a groundbreaking idea. If you have a lot of processing power, just waste it. Now, if you're in higher dimensions, there is not much chance for such an algorithm, because you would have to have a cloud of solutions around the solution of a heat equation. This is not feasible. But the one-dimensional idea is very clever, very clever. Then a lot later, there was a new idea by Bellin and Zenaro in 1989. And they have in their abstract the following saying: in addition to the two types of parallelism mentioned above, we wish to isolate a third which analogous to what Geer has more recently called, Geer was this research review paper, parallelism across the time. So you see, that's exactly what we try to do. We try to parallelize the computation along the time axis. Here it is more appropriately called parallelism across the steps. In fact, the algorithm we propose is a realization of this kind of parallelism. Without discussing it in detail here, we want to point out that the idea is indeed that of multiple shooting, and parallelism is introduced at the cost of redundancy of computation. We've also heard redundancy this morning. It might be worthwhile to do more calculations than necessary to save communication, for example. So here is the term multiple shooting, and this is the key ingredient of these methods. And in Nievergel's paper, multiple shooting was not developed yet. He did not have a means to use multiple shooting. It did not exist yet. So here is the idea of Bellin and Zenaro. They don't use an ODE. They use a recurrence relation, which you get from a discretized ODE. So you just have a law that gives you, when you have a y0, from y0 a y1, and then from y1 a y2, and so on. And this mapping is called F. And you have to go sequentially through to find this trajectory, discrete trajectory. But you can also collect all these values in a vector y. So now the vector y contains y0, y1, and so on. And then you write this recurrence relation simultaneously for all values. This you can do. So here is now the vector y, the solution you want, is a function of y, which you could evaluate sequentially, but you just write it for all values simultaneously. So this function phi, capital Phi here, in the first component, it's just y0, because y0 must equal y0. But then in the second component, it's f1 of y0, because you must get f1, y1. And then f2 of y1, because you must get y2, and so on. So this is a nonlinear system of equations. that you can try to solve for y. See, y equals phi of y. You can solve this system for y. For example, using Newton's method. Or what they do in this publication, they use Stephenson's method. Stephenson's method is an iterative method for this nonlinear system. Does actually anybody know Stephenson's method? I didn't know it either. First time this method occurred to me, I will explain it on the next transparency. You get an iteration like this. The new approximation is phi of the old approximation plus a Jacobian, like in Newton's method, or an approximation thereof, times the difference of the two approximations. And they start, because you need a vector to start, they just start with the constant initial y0. And then they iterate this thing. Now you see this iteration calculates at each step the whole trajectory at once, an approximation of the whole trajectory. So what's this Stephenson's method? It's a really clever method. I didn't know it. It's to solve a nonlinear equation, so f of x is 0. And it's almost like Newton's method. So you see you get a new xk plus 1 from the old xk minus a Jacobian inverse times f. But it's not the Jacobian. It's a finite difference approximation, and it's a really funny one, you see. Instead of using an h step to do a finite difference and choose a small h, you use f of x instead of h. So this f, if your method converges, becomes smaller. And you can prove this also converges quadratically, like Newton's method. I didn't know that. I think that's really clever method. Instead of having an h and then divide by h, you take the f, which is becoming smaller as you iterate, and you divide by f. And they prove the following results. They prove that at each iteration of this method, you get one more value of your trajectory exactly. You just get it. So there is some sequential integration that happens in this method. And this means if you've iterated as many times as you wanted to know time points, you will have the solution. This method can never fail. It will always get the solution. But it's going to be too late because it gets the solution the latest when you've sequentially gone through. So there's no gain as well, but at least it cannot fail. They prove, because it's a Newton-type method, that convergence is quadratic. So if you're close to the solution, this whole trajectory is going to converge at the early time points and at the late time points. It's just going to converge onto the solution.
Sorry, Martin.
Yes?
Can I ask you a very stupid question?
Yes.
So your f is a vector.
In my case here, I took a scalar. There is a vector-valued example as well, but it would have been a bit harder to explain. So I just chose a scalar. Yeah. But there's a vector with a matrix, Jacobian matrix variant as well of Stephenson's method. Yeah. So I just chose a scalar to make this very transparent and to remember what the method is. Yeah. So each of these corrections you can calculate in parallel, because if you remember the evaluation of f in this right-hand side, you just evaluate. There's no connection in between. And they get speedups of 29 to 53, they measure, for about 400 steps, which means you could use like 400 processors. So that's not a brilliant speedup. If you use 400 processors, you would hope to get 400 times faster, because you put 400 times more resources. But you will see throughout all these lectures, time parallelization is more something along these lines. There are few methods that get much better than this. So you waste resources. Yes, there was a question? This is written for the nonlinear case. Yeah, so it's a full Newton's, it's the Stephenson's method which is used. Yeah. So here we have a systematic method that sort of seems to be able to do this. And then there was a very fundamental contribution by Philippe Chartier and Bernard Philippe in 1993, a parallel shooting technique for solving dissipative ODEs. Here we have now the name in the title. It's a parallel shooting method. And they have in their abstract, in this paper, we studied different modifications of a class of parallel algorithms initially designed by Bellin and Zenaro. So you see clearly these are these two people I discussed before. For difference equations and called across the steps method by their authors, for the purpose of solving initial value problems in ordinary differential equations on a massively parallel computer. It is indeed generally admitted that the integration of a system of ordinary differential equations is a step-by-step process and is inherently sequential. So again, you see somehow there is no parallelism in this type of problem. The funny thing is this article appeared in a journal where they have a German abstract. It's a former German journal which still had German abstracts. So what's their method? Here we have now an ODE. So there's not just a recurrence relation, it's an ODE. So u prime equals f of u of 0 equals 0. We want to solve this in the interval 0, 1. And we want to use multiple shooting. Now, shooting methods were not developed for initial value problems. Shooting methods were developed for boundary value problems. So in general, for a shooting method, what you would do is you would have a second-order problem. You would have an initial condition. You would have a final condition. So this is u. This is x. We go from 0 to 1. We know the solution should start at A. We know the solution should end at B. And the solution needs to satisfy this second-order equation. Now, a shooting method would say, I don't know how to calculate this trajectory, but I know how to calculate the trajectory with a second condition at 0, a slope. Because that's now an initial value problem. For initial value problems, there were many methods, Euler, Runge, Kutta. So, but you don't know what S is. S is the slope here. So you just start with some S, and you shoot. Oops, that was too high. So the angle was too large. So you do a smaller angle. You try like this. Oops, that's too low. So you should go somewhere in between. So you shoot here. Now you see why it's called a shooting method. Because you really shoot at a target, and you try to hit this target. Now, the problem is, in our case, we have an initial value problem. We don't have any target. We just have a condition on this end. There is nothing to shoot at. In our case, the problem is actually this. If I write this as a system, that's what we try to solve. So how can you shoot in that case? You can shoot if you try to do multiple shooting. So you introduce time subintervals. In my example, I introduced 3. I want to solve this problem on the first interval with a given initial condition, which I here call capital U0. I assume I don't know what it is. I want to solve it on the second interval with an initial condition I call U1, which I don't know what it is. And I also want to solve it on the last interval with an initial condition that I don't know what it is. So these are the shooting parameters. And because I have now 3 intervals, I have 3 conditions I have to satisfy. The first shooting parameter should be the initial condition of the problem. The second shooting parameter should have the value where the trajectory arrives on the first interval after an interval of 1/3. And the last shooting parameter should have the value where the solution of the middle interval arrives after having passed through its interval. So you see, I have 3 equations for 3 unknowns, capital U0, capital U1, and capital U2. So I can collect these 3 equations as a vector equation f of u, which is this, this, and this, equals 0 for the unknown 3 values. Now I have a nonlinear system of equations, which I would solve using Newton's method. So what happens if I apply Newton to this system? That's now a multiple shooting method for an initial value problem. So there is a copy of the system up there that I want to solve. Newton's method calculates a new approximation at step k plus 1 from the old approximation at step k minus the Jacobian inverse. You can see this is the Jacobian, this is the derivative of this function up there with respect to u0, u1, and u2. So you get 1 on the diagonal, and you get the derivative of the solution with respect to the initial value at the end of the interval in the subdiagonal. And then here you have the evaluation of f at iteration k. So that's a plain Newton method to solve this nonlinear system. Now, to see how this looks like, I just multiply this matrix here through on the other side. So this term here will not have a matrix anymore. and this terms here will get the matrix. And I use the bidiagonal form. Then I get a recurrence relation that looks like this. The first shooting parameter is always U0. That makes sense because I know the initial condition. The first one should never change. Now the second shooting parameter equals, in this Newton iteration, the solution on the first interval at the end, given a shooting parameter U0, plus a Jacobian term times the difference between two iterates. And it continues like this. So this method I can also write for n intervals, where this is now the interval count, this is the Newton iteration count. The new value I get from an exact solution on each interval, plus a Jacobian term evaluated at the old shooting parameter, times the difference between new and old. That's a multiple shooting method. Now, maybe I can point out something important here. This here is an exact solution on each interval. But because I know the initial condition from the previous iteration, this can be all done in parallel. Here, there is also the new iteration of Newton. The new iteration is here and here. So this cannot really be done in parallel. This sort of depends on each other. But this can all be done in parallel. So how would that work? Here's a cartoon. We've seen that the initial condition is always the same. It's the correct one. So no matter what I do as the first iteration, this is going to be the exact solution. This will start somewhere at an initial guess. This will start somewhere at some other initial guess. But the first interval is going to be exact. Now, in the next step, this endpoint is exact. So the second interval necessarily has to become exact, because it starts with the correct value. And in the next iteration here, we have the correct value. So necessarily, even if you don't do Newton, any fixed point iteration, reasonable fixed point iteration, would give you the solution. So in 3 steps, we'll have the solution. That's like in the method we've seen of Bellin and Zenaro. These types of methods, they just give you the latest after n iterations the solution. But can they do better? Because there's no interest. If you use 3 processors, and if you iterate 3 times, you have done 3 integrations sequentially, so there's no point. So it must be faster than this, otherwise there's no interest. Now, Chartier and Philippin, they showed that for certain problems, it can go faster, but for certain other problems, it might not go faster. And here is an example from their paper. So here is the time axis. The exact solution is a solid line. It's the solid line. You see, it's an oscillatory solution. It's a non-dissipative example here. It's an OD. And the first iteration of this multiple shooting is the dotted line, which is pretty close. The second iteration is further away from the solution. So in that case, the method does not seem to work. It will eventually, as you see, it gets the first correct, the second correct. So if you march through, it will get the solution, but it's not contracting, even though there's a Newton method running. So there are properties of the system that make it not work. But if the system is the dissipative problem, and they prove this, then you get convergence quadratically on the whole length. You get the solution much faster than going sequentially, and the much faster depends on your problem. So here is a problem where the much faster is not too bad. If you use 100 processors, you get about 14 times as fast, but then eventually it's not getting any faster. Here is an example where with 100 processors you get about 3 times faster, 3.5 times faster. You still get faster. If somebody would have asked you before my lecture, can you go faster than sequentially, most of you would have said no. You can, but not for all problems. So that's a very groundbreaking contribution. And the next very important contribution is by Saha, Stadel, and Tremaine. They come from the application area of solar dynamics and planetary dynamics. And they say we describe how long-term solar system orbit integration could be implemented on a parallel computer. The interesting feature of our algorithm is that each processor is assigned not to a planet or a pair of planets, but to a time interval. Thus, the first week, second week, up to the 1000th week of an orbit are computed concurrently. the problem of matching the input to the n plus first processor with the output of the nth processor can be solved efficiently by an iterative procedure. And then they say our work is related to the so-called waveform relaxation methods. So this is a type of method that I will discuss in the next lecture. But here they already point out a relation. I will not explain the quadrature formula the way they got their idea, but I show you what they do. They solve a Hamiltonian problem because planetary motion is a Hamiltonian system. There is energy conservation, there is symplecticity as well. Hamiltonian systems you can write with a Hamiltonian h, and there are two components, p dot equals minus h derivative with respect to q, and q dot equals h derivative with respect to p. That's a Hamiltonian system. So the Hamiltonian for planetary motion can be written as I wrote it above. There is a major part, h0, and h0 depends on the sun attracting the planets. That's the strongest force that makes planets go around the sun. And then there is a small second term in this Hamiltonian, and this term describes interaction between planets. Planets also attract each other, but the influence is very small. The main force comes from the sun. So in the solar system, this is a typical Hamiltonian. Now, if we collect the unknowns p and q in a y, and the right-hand side's h, q, and hp in an f, then this is just a system of ODEs like the ODEs we've seen before. So in particular, one can write a multiple shooting method, like the one of Chartier and Philippe. So here is Newton's method applied to this problem. After multiplying through by the Jacobian, you get the new approximation at Newton step k plus 1 at time interval n plus 1 equals the exact solution on the previous interval, plus a Jacobian term, times the difference. And now there's the key new idea that comes here. This Jacobian term is a derivative of the original Hamiltonian system with respect to the initial condition. And the original Hamiltonian has two components, an important one and a small one, depending on epsilon. And what they do now is they say, we do not calculate the exact Jacobian here. We only use the Hamiltonian for the sun, because that's an integrable system. We can evaluate this exactly. And we don't even calculate the derivative. We say a derivative applied to the difference can be approximated by the difference of two trajectories. This you just get from Taylor expansion. If you expand this term here aboutynk, then you get first this term, and then next you get this term. So that's a key new idea. They don't calculate the Jacobian on the exact problem. They calculate an approximate Jacobian, and they don't even calculate the Jacobian, they make it a difference of trajectories. And they prove that now this method does not converge quadratically anymore, but at each iteration, they gain an accuracy of a factor of that epsilon which they dropped in the approximation. So here is an example where they verify that they get accurate trajectories. Here is an example where they show how many processors they used and corresponding how many iterations they need. And you see, they don't need many iterations. They don't need many iterations. With 10 processors, they need 4. With 100 processors, they need 5 or 6. With 1,000 processors, they might need 7 or 8. And now there is this seminal paper coming by Lyons, Madé, and Torinici in 2001. I saw this paper very early on. Laurence Alpern asked me to read it and tell her what I think about it, so I read it and I didn't think much about it because I saw it's converging step by step like we've seen in all the other methods. I didn't see anything else that would be interesting. So here is the description of the method. They describe it for a scalar problem. And they say the name of the method, elle a pour principale motivation les problèmes en temps réel, d'où la terminologie proposée de para-réel, parallel method for real-time problems, para-réel. So 15 years ago, if you searched para-réel on Google, it would have told you, did you mean parallel? Now, if you search para-réel, it's going to give you hundreds, thousands of references. So what's this method? So for an ODE y dot equals minus ay on the interval 0t with a given initial condition, you first use a backward Euler method to get a rough approximation, like in Nievergeld, a rough approximation of the solution. And then the recipe says you calculate exact solutions of the underlying problem on each time interval, starting at these approximate values. And now there is a complicated recipe following. You have to compute jumps, which are differences of the exact values minus the approximate values you had. Then you have to do a forward Euler propagation of jumps with the jump at the right-hand side. And then you have to update the values you got. This method was invented in this form using the idea of virtual control of late Lyons. But it's not clear what this method does. It's very difficult to understand what it does in this form. So, what do they do in this paper? C'est alors un exercice que de montrer la proposition. The parallel scheme is order k, which means that there exists a constant c that depends on k, such that the error after k iterations of this algorithm is bounded by this constant, which will depend on k, times delta t, which is the interval of these shooting steps that you do, to the power k. So remember, I started with an Euler method. That's an order 1 method. If you do one iteration, you get an order 2 method. If you do another iteration, you get an order 3 method, and so on. But there's a constant in front here, which is not specified. So here they don't look at how this method converges as an iterative method. They just look at, if you do 4 iterations, what order of a method do you get? And from an Euler method of order 1 with 4 iterations, you get 4th order. Now this method can be written in another form, which has established itself in the years following this publication, because there was a lot of interest in this method. And the best way to write it is as follows. So I go back to my notation u prime equals f of u that I want to solve. It needs 2 ingredients. It needs a coarse propagator. This is an integrator, which takes an initial condition u1 at t1, gives an approximate solution at t2, very cheap, 1 step of forward Euler. Must be very, very cheap. It needs a fine propagator, f. This does exactly the same. It takes an initial condition starting at t1, gives a solution at t2, but it's very accurate, very expensive. And then if you rewrite this method with propagating of jumps, you just rewrite it. You work, you find this recurrence relation here. And now you see this looks bloody like what we've seen before. You get the new approximation at iteration k plus 1 by an exact or very accurate solution, plus the difference of a very coarse approximation. So that was the first result that we proved. Now it looks like completely trivial, but it took us a while to figure this out. This is just a multiple shooting method, where instead of applying Newton, you approximate the Jacobian in Newton on a coarse grid. So not like in Saha et al., where they removed part of the Hamiltonian to make it cheap. It's just on a coarse grid. That's what it is. So the parallel algorithm is a multiple shooting method for an initial value problem where the Jacobian is approximated on a coarse grid. That's it. Now here is a convergence result that I like a lot because it describes all the properties of this algorithm in one result. I worked on this quite hard. I had it first for a linear problem we published with Stefan van der Walle. Then I tried for a nonlinear problem. I got it going. I presented it in our seminar in Geneva. And then Ernst Heirer, at the end, he said, I think you can simplify this proof. And then he showed me how. And the proof is now about a page long. It's very elegant. It uses generating functions. I learned a lot doing it. So what does this result say? There are some technical assumptions which are satisfied. It says that the error after k steps is related to the initial error. I take the maximum over all time intervals by 3 factors here. Now let's first look at this factor. This is a product that goes from 1 up to the number of iterations I did. So at the first iteration, this multiplies the error by n minus 1. So that's very bad. The initial error could be multiplied by n minus 1. After the next iteration, it's going to be multiplied by n minus 1 times n minus 2. That's even worse. So this part in the boundary goes up like crazy. Why is it important? Because if I iterate n times, if k here is n, then the last term in this product is 0. So this term tells you the latest you will converge is after n iterations. So this result contains that property of the algorithm. But it contains more. It contains these two terms. This is a benign term. It's 1 plus some small term to the power n that's going down. But this is the most interesting term. This says delta t to the k times p plus 1. This result is for a method of order p. So if it was Euler, p would be 1. Second order p would be 2. So at each iteration, you gain an order, like in the result of Yvon-Madé. But in addition, you divide by k factorial. Now, this k factorial here, it's growing faster than any constant to the power k. So even if this is a big constant to the k, eventually this is going to be dominating. This shows superlinear convergence, and that's a waveform relaxation type convergence result we will see later. If I rewrite this, I can also get exactly the result of Yvon-Madé, but for the general case of a pth order method. And I also have the constant. This is the exact constant c depending on k here, with everything depending on the constants in the assumptions. So that's a very accurate result. Now, does this work? Here is an example that was suggested by Jean-Pierre Ekman in 2004, who was in a seminar that I gave in Geneva at that time. And at that time, I told the audience, this is to calculate problems in real time. For example, weather prediction. Because if your weather prediction is only finished calculating tomorrow, it's not a prediction anymore. And then Jean-Pierre Ekman said, but you don't have any example. You should do at least Lorentz equation. Because Lorentz equation was the first weather prediction model. Very, very simple. A 3-dimensional problem. There's just 3 unknowns. It's nonlinear. And it has the butterfly attractor. So I did this just to see if it works. And this is an interesting cartoon of how the iterates converge. So there are 2 panels on this. The top panel shows the 3 coordinates. So you see the oscillations which correspond to the oscillations in the butterfly wings. And the solid line is the exact solution, which you can calculate only to about t equals 10 in double precision. And the dashed line is my first approximation from this method on the coarse grid. It's a Runge-Kutta 4-order method. So you see, at the beginning, it's quite good. But with this chaotic nature, very quickly it gets wrong. It even gets into the wrong wing of the butterfly. The errors are very large. And I plot the errors on this panel. So you see the errors are basically order 1 on the whole time interval. I also added a line here, the red line. This red line says how far I would have gone with 1 processor. So I use about 180 processors here. And if I do 1 iteration with these 180 in parallel, if I had only used 1, I could have integrated up to here. And the dots up there show the same. So now I start iterating this parallel method. So you see it starts iterating. It's still in the wrong wing of the butterfly, still in the wrong wing. Now it's in the right wing of the butterfly. Sequentially, I could have gone up to here in the same time. In parallel, I've calculated up to here, but it's still error order 1. And now this interesting thing starts happening. You start see contraction uniform on the whole time interval. The error goes down. You see, sequentially I could have gotten up to here. And with this algorithm, I have an accuracy of 10 to the minus 5 up to here. So this does work. I can get this solution faster than sequential and quite a bit faster. But I'm burning processes. I burn 180 on this. But you see, this is a working method for this problem. Here is a second example. That's the Arenstorff orbit. It's also a very fun example. If you were on the moon, and if you shot a satellite exactly at the right angle and with the right speed to try to get back to Earth, if you get it wrong, the satellite is going to miss the Earth. It's going to do a really strange loop, another loop, another loop, and it's going to come back to the moon. That's called an Arenstorff orbit. So I calculate this Arenstorff orbit with the parallel algorithm. So you see the initial Euler approximation. It's completely wrong. It's just a spiral outwards. Error is order 1. But already the first correction of this parallel correction gives you an approximation that's quite good, even better. And you see the error goes down, 10 to the minus 8, 10 to the minus 10, 10 to the minus 12. So here is a summary of this first lecture. We've seen the methods that I put on this transparency. And given the time I've spent, I would say we should definitely start at 3 again, so you have about 8 minutes break. Thank you. So I will start the second lecture. The second lecture is about waveform relaxation and domain decomposition. You've seen already in the first lecture that waveform relaxation appeared as a name. So this is a lecture about the red track, waveform relaxation and domain decomposition. So you see these are iterative methods. The first versions of these methods go much, much further than Numerical back in time, Picard and Lindelöf. Then there was an engineering contribution, very important, and then I worked a lot on this alone in my thesis, and then with Frédéric Nataf and Laurence Alpern. And there is more recent contributions last year and 2 years ago. So what are these waveform relaxation methods? One of these methods you must have seen in an ODE course. It's a way of proving existence and uniqueness of solutions of ODEs. And it's Picard who invented a way to do this. It's in a paper sur l'application des méthodes d'approximation successive à l'étude de certaines équations différentielles ordinaires. So here we have v prime equals f of v with the given initial condition. You first write this as an integral equation. So this would be v at t equals v at 0 plus the integral from 0 to t f of v, tau d tau. And Picard, because he could not figure out if this equation has a solution, wrote this equation as an integral equation and said, because I can still not solve the integral equation, I just do a relaxation. So I start with the v0, which I suppose I know. Then integration is easy. Then I add the initial condition, and I find a new approximation. And with this new approximation, I go here again. Integration is easy. I add the initial condition, I get a new approximation, and I iterate like this. This was the méthode des approximations successives de Picard to find the solution of this equation. And Picard proved convergence of this method to a limit that satisfied the ODE. And with this, he proved existence of the solution of this ODE on an interval from 0 to t. And a year later was Lindelöf who gave a convergence estimate for this iteration. And this is a very, very famous convergence estimate. It says if you iterate this Picard iteration n times, then the distance between the solution of your ODE and your nth approximation is bounded by a constant times capital T to the power n is the number of iterations, divided by n factorial, times the distance of the initial guess that you used of the true solution. Now, if you remember from the previous lecture, this factorial I had as well. K was the iteration of Newton. This power I had as well. So a parallel method is a method somehow that has inherited this type of convergence behavior. But there were other terms. So this is a typical convergence of this fixed point iteration applied to initial value problems. But that's a theoretical tool. That's not made as a method to solve this equation. And in a textbook of Milne in 1952, he says explicitly he would never recommend such an iteration to actually try to solve an ODE. It's not an efficient way to do. Nevertheless, in the engineering community, this is always falling. In 1982, there was a major invention for VLSI design by Lehrer Rasmi, Rioli, and San Giovanni Vincentelli. And it's nice, these IEEE papers, they have pictures. So you can see how they look like. This is Lehrer Rasmi, this is Rioli, this is San Giovanni Vincentelli. Rioli was a Swiss. He worked for IBM Rüschlikon. then emigrated to the US, worked at the IBM lab in Yorktown Heights until he retired. I got to know him when I started working on these methods. And since I knew he was originally from Switzerland, I started to babble Swiss German to him. And from deep down under, there was Swiss German coming back. It's been 30 years he had not spoken Swiss German, but he still knew it. I meet him occasionally. He had a skiing accident this spring, but he's fine. He had surgery and he's going okay. He's been retired for about 8 or 10 years now. He's a very nice guy, very good skier. And here they write in their paper why they tried such a waveform relaxation method. The spectacular growth in the scale of integrated circuits being designed in the VLSI era has generated the need for new methods of circuit simulation. Standard circuit simulators such as SPICE and ASTAP simply take too much CPU time and too much storage to analyze a VLSI circuit. And the concrete problem was that the next generation of processors had so many transistors on it that they could not simulate the whole thing on the current generation of processors. There was not enough memory and not enough computing power. So they tried to find a method to simulate this too big new generation on the current architecture. And here is the original example they had. It's a Moss-ring oscillator from 1982. The circuit that has 3 voltages that are measured, V1, V2, and V3. There is ground here, here, and here. There is a feedback loop that comes from the last voltage to the gate of the first transistor, and there is a voltage source here that drives this Moss-ring oscillator. Now, why is this a Moss-ring oscillating circuit? Suppose this V1 is at 5 volts. If this V is at 5 volts, it connects to the gate of this transistor. If you have a voltage on a transistor, the transistor will open, which means there is going to be a wire connection to ground, which means V2 must be at 0. If this V1 is at 5, this V2 must be at 0. Then there is a 0 at this gate of the transistor. This transistor will close. So there is no wire connection to ground, and V3 is going to be pulled up to 5 volts. This means V3 is at 5 volts. Now 5 volts is going to be fed back into the gate of this transistor. This means this transistor will open. So we had 5 volts there, but because it will open, it will connect to ground, it's going to go down to 0 volts. And now you can see how it oscillates. 0 is going to close this one, it's going to pull up to 5. It's going to open this one, it's going to pull this down to 0. It's going to close this one, it's going to pull up. So this is why it's a Moss-ring oscillating circuit. And they wanted to simulate such a circuit, not this one, a huge circuit with like millions of voltage points. But they use this as an example to explain their method. If you use Kirchhoff's and Ohm's laws, you can write the system for these 3 voltages of ordinary differential equations with some initial condition. So V contains 3 unknowns. And it simulates the up and down of these 3 voltage values. So their idea of waveform relaxation is, suppose this circuit is too big to be simulated. Let's partition it into smaller circuits. So here is one circuit, and this wire was now chopped. There was a wire connection here to this gate, it was chopped. Then there's a second circuit, and the connection was again chopped. And also the feedback loop was chopped. But certainly this cannot have the correct solution anymore. It's not possible that this is the same solution. So as an engineer, you add voltage sources along each wire that you chopped, which should feed in the signal which was missing because you chopped it. And what you feed in is just the value that you get from the previous iteration of the algorithm. So if I do this for the system of ODEs, here you see the system written for the 3 voltage values. I solve on the first system, the ODE like it was, but these 2 values, because the wires have been chopped, I just feed in the value from a previous iteration. So initially I can start with 0, for example, or 5 volts, or anything. And this I can solve simultaneously with this one. This is the middle system, which I solve for the middle voltage, and I just feed in where the wire was chopped, neighboring values, which I don't know what it is, at the first iteration, just some guess. And the last one as well. Now, because the signals that travel along wires are called waveforms in electrical engineering, and these waveforms, instead of taking the really one that comes, we take a relaxed one from the previous iteration, these methods are called waveform relaxation. That's the name they gave to these methods. And you can see this is a parallel variant. I can solve all the three in parallel because I relaxed both neighbors. One could also use k plus 1 here and k plus 1 here, then it would be a sequential. And now you recognize this is like a Jacobi relaxation in linear algebra. And if I took k plus 1 here, it would be like a Gauss-Seidel type relaxation. But we don't solve a linear system, we solve a system of ODEs at each step. So this iteration produces a solution in time. Then it exchanges information. It produces a solution in time. It exchanges information. How does it converge? Here is a convergence study they did. They had no clue how this would converge. And we know it's an oscillating circuit. And you see after 1, 2, 3, 4 iterations, they actually have the solution. 4 iterations it takes on this length of the time interval to get to the solution. But if the time interval was shorter, if the time interval was only 1, you would basically get it after 1 iteration. Or if the time interval was like 1.5, you would get it after 2 iterations. So you see this method, the shorter the time interval there is, the faster it will converge. That's waveform relaxation. Now I want to show you how domain decomposition comes in these time-dependent problems. And to do so, I first explain the 3 classical domain decomposition methods for steady problems. The first one is the Schwarz method. You've seen the Schwarz method this morning. I use a very simple example like Frederick did, but I don't even have a right-hand side. So this is directly the error equations that Frederick had this morning. So I take Laplace's equation on the interval 0, 1 with homogeneous boundary conditions. So the solution is 0, I want to calculate. And I do a Schwarz method, which means I decompose the domain into 2 subdomains. You see one subdomain and the second subdomain. The overlap is from alpha to beta. And I solve on the first subdomain my problem, starting with some initial guess, u20 here. Laplace's equation has a straight line as the solution, so this is my solution. Now I grab this solution at this interface to solve on the second subdomain. So I solve. I get a straight line on the second subdomain. Now I take the solution here again and solve on the first subdomain. And on the second subdomain. So you can see how this method converges. That's the classical alternating Schwarz method. We've seen a parallel version due to Lyon's. If you put just an n-1 there as well, you calculate the same sequence, just double. Now there is another basic domain decomposition method, which is called the Dirichlet-Neumann method. This was invented much, much later than the Schwarz method, about 100 years later, by Björstad and Widlund. Björstad is organizing the next domain decomposition conference in Spitsbergen. It's going to be in February. Spitsbergen is 2,000 kilometers north of Norway. In February, there is permanent night there. So if you want to go to a conference that you will never forget, and where you don't have jet lag, go to that one. You can sleep anytime. So this is the Dirichlet-Neumann method. What's different between this method and the Schwarz method? The fundamental difference is that you exchange a Dirichlet value on one subdomain, like for the Schwarz method, but the other subdomain will use a Neumann value, and there is no overlap. So the first solution here is exactly like in the Schwarz method. You see, the subdomains do not overlap. And now you have to produce a solution on this subdomain that has this slope at this point. How does this solution look like? Can you picture this? It must be yeah, exactly. It must be a straight line that has the same slope as that one. So that's what the second subdomain does. Now we have solved on the second subdomain. Now, this value here will be used by the first subdomain as a Dirichlet value. So you need to get a straight line here. Now, this slope will have to be used to produce a solution here. Now, you can see this must make something like this. And you can see it works. You see this will spiral in. It will converge to 0. Schwarz method converges like this. This converges like this. But what happens if I move alpha? I put alpha to the left. So now suddenly my Neumann domain is bigger than the Dirichlet domain. I start again with a value. I pick this slope. I have to make a solution on this interval with this slope. Here is the solution. I have to pick this Dirichlet value, evaluate. I have to do a solution with that slope on this domain. Now you see, oops, here it actually does not work. So you see, if the Neumann domain is smaller than the Dirichlet domain, it spirals in. But if the Neumann domain is bigger than the Dirichlet domain, it spirals out. That's not like the Schwarz method. The Schwarz method will always work for your overlap. That's why in these methods, you need a relaxation parameter. You cannot just do a Neumann solve, a Dirichlet solve, a Neumann solve, a Dirichlet solve, a Neumann solve. What you have to do is you have to introduce a relaxation parameter. So now instead of starting directly with the solution from the other subdomain, I start with a value that I call h. There's an h0 I solve. I take that slope, I solve the Neumann problem. But now I don't take this value here to continue solving, but I take an average of this value and the value I had before. You see, it's theta times this value, and 1 minus theta times what I had before. So I take something in between here, and then I get my new h. Now you see, there's actually something brilliant about this method. If I choose my theta such that the average of these two is close to 0 or even exactly at 0, this becomes a direct solver or a very rapid solver. So this relaxation parameter is very important in this method. You can make it work. Without this, it's not going to work in general as an iterative method. Then there is the third domain decomposition method, which is called Neumann-Neumann. It was invented around at the same time in France, Bulga, Glowinski, Dalek, and Vidrascu. And this is a method that has not alternating steps, but it does double steps. So the first step, you solve on both subdomains a Dirichlet problem. So you start with some initial guess, you solve a Dirichlet problem here and here. So that costs twice as much as the other method because you have two solves. But then you calculate the normal derivatives that you get here and here, and you impose their sum as a Neumann condition again on both subdomains. So these have the same slope, these two. Now we've calculated psi's on the two subdomains. So we first had two Dirichlet problems, and then two Neumann problems. And here you can see this cannot possibly work. You need a relaxation parameter. But again, if you take a relaxation parameter to take some average of these values to subtract from this value, you can actually make this into a fast method. You can get the H1. If you take exactly the correct value in 1D, you can make this H1 be here, direct solver. So these are the three methods that are known in domain decomposition. The first one gave the Schwarz method also in higher dimensions, gave the additive Schwarz variant, which is not an iterative method, gave RAS, ORAS, optimized Schwarz methods. The second method that does Dirichlet on one subdomain, Neumann on the other, did not propagate very far, because it's really annoying if you have many subdomains to decide which one should do Dirichlet and which one should do Neumann. It's just annoying. Whereas this one went very, very far. This method here became fetty if you do first one solve and then the other, or Neumann-Neumann, balancing Neumann-Neumann, if you switch the order. These two methods are basically the same. So this method went very, very far. So my interest here is in time-dependent problems. So I want to understand, how do these methods converge if I solve now a heat equation or a wave equation? So you see, I have spaces before here, but now I have a time dimension here. And for a Schwartz method, I would pose overlap between alpha and beta, like in the Schwartz method for the steady problem. But the problem I want to solve is now a space-time problem on the subdomain. So I start with some initial guess along this timeline, and I solve in space-time. Then I extract the solution here and solve in space-time, and I alternate like this. Why could this be a good idea? We've heard this morning that processing power is really almost free these days, whereas communication is getting annoying. Now you see, this method has a much better volume computation to communication ratio than if you did time stepping. Each time step does not give much computation. And then after each time step, you would have to iterate between the subdomains, and then do the next time step iterate. In these methods, you solve a whole space-time problem, a lot of computation, and then you once send data of this interface to your neighbor. So that might be one of the interesting things this algorithm has. If it's a non-overlapping method, like a Dirichlet-Neumann or Neumann-Neumann, I can also solve space-time problems now, and alternate, or do 2 Dirichlet space-time followed by 2 Neumann space-time. So how does these algorithms behave? I start with the result for the wave equation. It's an interesting result. So I apply this algorithm in the Schwartz variant, so I call it Schwartz wave formalization, to the second-order wave equation, which means I solve on my first subdomain in space-time the wave equation with some initial guess. I give the trace to the neighbor. I solve the wave equation on the second, and I go back and forth. This is an algorithm I looked at in my thesis, and it's a direct solver. It converges after a finite number of steps. As soon as the iteration number n is bigger than the length of the time interval times the speed of propagation of the wave divided by the overlap, you have the solution. And this is not only true for this one-dimensional example, this is true in full generality. It's a direct solver. You can also do an optimized variant, which can also be made into a direct solver. I'd like to prove why it converges in a finite number of steps, and it's a drawing, the proof. So it's a hyperbolic problem, this wave equation. Hyperbolic problems have a finite speed of propagation. And so if I look at the first solve on omega 1 in space-time, I know the initial condition here, because it's given by the problem. I also know this boundary condition is given by the problem. The only thing I don't know is what should come from the other subdomain along this line. So along this line, in my first iteration, I'm going to have an incorrect value. Now, this incorrect value can only propagate at a finite speed into the domain. So as long as I'm below this characteristic, which is given by the wave speed of the equation, below here I have the exact solution. Because this error cannot propagate faster than this characteristic line into my domain. So in my first iteration, I have the exact solution here, and here I'm going to have garbage. This is all wrong. But this means when I give data to omega 2, along this line, the solution is going to be correct. Only above here, it's going to be wrong. So the second subdomain is going to have the exact solution under this characteristic. And now you see why it converges in a finite number of steps. Because now I have the exact solution along here, and it's going to be exact up to the end of the green line. So if my interest is only a time horizon, a time interval of this length, I need 2 iterations, and I have the solution. So for this type of equation, it's a direct solver. And this also shows you how you should use it. You should use it such that you basically have one solve in each subdomain, and then you have to fix the overlap. That's a good way of scaling this algorithm. It scales to many subdomains, no coarse grid needed. It's a perfectly scalable algorithm for the wave equation. Here is an example with non-matching grids. That's another advantage of these types of methods. Here is time, here is space. I have 6 subdomains, and you can see I have different wave speeds in each subdomain. Now, for a wave equation, it's very important to be close to the CFL condition with your discretization to have an accurate solution. So I choose different space-time meshes that I'm close to the CFL condition, and then I solve with this waveform relaxation algorithm. I have an initial signal here, which propagates throughout the whole domain, which is reflected at these interfaces because these are real interfaces. It's a different material, different wave speed, so you get reflections. And I calculated this with an optimized Schwartz waveform relaxation algorithm that uses different time steps in different subdomains, so non-matching grids. How does the Dirichlet-Neumann waveform relaxation algorithm for the wave equation behave? So here I just copied the algorithm that I explained to you in the steady case. You start with some initial guess, but you do it in space-time. And then you do a Neumann solve in space-time on the second subdomain. Then you do this relaxation, and you go again. This was a topic of Bankim Mandal, who did his PhD in Geneva. And there is interesting things one can show. One can show also this algorithm converges in a finite number of steps. It's a direct solver. It depends on the choice of the relaxation parameter. It also depends on where your interface is in this simple one-dimensional setting. So if the interface is exactly in the middle, and if theta is exactly a half, then you get the solution in 2 iterations. If the interface is not in the middle, and theta is a half, then you get a finite number of steps of convergence. It's the direct solver. And if the interface is in the middle, but theta is not a half, then you don't get a direct solver. So theta half is key for this algorithm. If theta is not a half, you lose a lot in this method. We also studied the Neumann-Neumann waveform relaxation algorithm for the wave equation, and the results are very similar. It's a direct solver under certain conditions of alpha and theta, and if theta is not well chosen, it again converges only linearly. So these methods are domain decomposition methods that are used in a waveform relaxation type. They solve in space-time, and for the wave equation, we don't have a full understanding. They're all direct solvers for good choices of parameters. Now, this slide is containing results for about 10 years of work. This is the study of convergence of these algorithms for the heat equation. This is pretty hard. This is a lot of kernel estimates. The first of these results I got in my thesis for Schwartz waveform relaxation for 2 subdomains and n subdomains. You see the convergence is exponential, so it's super linear. It's an error function complement. It depends on the overlap. You see beta minus alpha. It depends on the length of the time interval. If the time interval is short, it's really fast. If the time interval gets longer, they get slower. It works for 2 subdomains and n subdomains. All these algorithms are waveform relaxation type, but you don't see the 1 over iteration number factorial. There's no 1 over n factorial in these. Where I've shown you before, waveform relaxation algorithms usually converge like 1 over n factorial. If you expand this using Stirling formulas, any of these results, you see all those are actually faster than 1 over n factorial. So it's the heat kernel that gives additional convergence speed for these methods. The type of convergence is the same if you use Schwartz waveform relaxation, Dirichlet-Neumann waveform relaxation, and so on. But the Neumann-Neumann and Dirichlet-Neumann waveform relaxation have in the argument of the error function or the exponential, they have no overlap length because there's no overlap length. What they have is the domain lengths, the subdomain lengths. So they have an advantage. Dirichlet-Neumann, Neumann-Neumann have an advantage over Schwartz waveform relaxation. These are the classical variants. This morning you've seen one can do optimized Schwartz wave methods. So you can add an operator here. Like Frederick explained, you can use a Robin condition, you can use a second order condition, you can use time derivatives. We've studied these methods over the last 15 years. There are many, many results. Many people have worked on this. These algorithms are reinvented as well in different contexts. For example, Björn Enquist invented the sweeping preconditioner. It's an algorithm of this type. Jimin Chen invented the source transfer 2 years ago. It's again an algorithm of this type. It just has a very good operator here. And I don't want to explain more details, but I want to show you a movie to show you the difference between a classical Schwartz waveform relaxation and an optimized Schwartz waveform relaxation method. So in this graph, you see the X domain here. And you see the subdomains. There is 1, 2, 3, 4, 5, 6, 7, 8 subdomains. You see the overlap between subdomains. And you see here the solution I try to calculate. And because it's a time-dependent problem, it will be a movie. It's an advection-reaction diffusion equation. This is the initial condition you see. And this solution will be advected from left to right. And it will be smoothed by diffusion. And we will form a boundary layer here. And I calculate the exact solution. And then as a dashed line underneath, what the first iteration of a Schwarz waveform relaxation algorithm would give if I start with a 0 initial guess to start the solution. Then I show the second iteration, third iteration, and you can look how such a method converges. So you see, the red solution is the solution I tried to get. The blue solution is the one I get from the first iteration of Schwarz waveform relaxation. You see, it's very bad. I basically missed most of the signal. That's because I imposed a 0 condition here, but I didn't know anything better in the classical variant. But if I do the next iteration, look at the beginning, the solution is actually quite good. It's only once your time interval gets longer, the solution gets bad. That's this typical waveform relaxation behavior. On short time intervals, convergence is good. On long time intervals, convergence is bad. But the method will eventually work. It's the next iteration. But you need many iterations. Now I'll show you exactly the same computation, but with an optimized transmission condition. So the rest of the code is the same. I just have a tailored transmission condition. And if you look at the first iteration, it's miraculously good over a whole time interval because it used an absorbing condition. Absorbing equals 0 means the signal can go out, and the next subdomain just takes it. So that's the difference between a classical and an optimized Schwarz, or classical and optimized Schwarz waveform relaxation method. Very important. Now, I just want to explain, before stopping this lecture, a combination one can do between domain decomposition and parareal that we've seen in the first lecture. So I have now space here, I have time here, and I decompose space-time. So I have many, many subdomains in space-time. And when I want to solve on this subdomain, for example, I solve all the subdomains in space-time in parallel. When I solve on this subdomain, what I will need is an initial condition, and I will need boundary conditions here. Then I can solve. Now, such a parareal Schwarz waveform relaxation method, what would it do? It takes the initial condition from a parareal iteration in time, and the boundary condition from the neighboring subdomain, like a Schwarz, classical or optimized Schwarz method. So this is a method that iterates in space-time. It was already proposed by Made and Turinici, but they iterated in space to convergence before doing a parareal iteration, whereas I just exchange with everybody and iterate space-time. This is the formulation. I will not show it. It's just a cartoon of how this algorithm runs. Here is time going forward. Here is space. I start with some initial profile, which is diffused over time. And I run this algorithm to show you how it behaves. So in the left graph, you see the approximate solution, which is calculated using 10 time intervals and 6 spatial intervals. So I have 60 processors that run on this. And each processor calculates on its space-time subdomain whatever it can calculate given an initial condition from parareal and a boundary condition from the neighbors. And here is the error of this first iteration. So you see, in the first iteration, not much happens. These subdomains have something to do, but here there's nothing interesting to calculate. But as iterations progress, you see the error goes down. This diffusive solution is advancing, but it's not a very fast algorithm. In particular, what you see is the parareal contribution that comes in time is more efficient than the waveform relaxation contribution in space. But here I use the Dirichlet classical condition. So eventually this method will converge. But if I use an optimized condition at the interfaces in space, then the first iteration, you see, it propagates already the whole time interval correctly, because now this is an absorbing condition in space. And this converges much, much faster. This is a space-time solver, which has a reasonable performance. So here is a comparison. This is when you use optimized conditions, and this is if you use classical conditions for this parallel Schwartz waveform relaxation method. So here is a summary of what I told you in my second lecture. I think we can have a break of about 20 minutes. We can start again at 4, and now there should be actually coffee ready, I think. Thank you.
In the parallel
Schwartz waveform relaxation. Yeah.
No, I don't remember my question. Oh, okay, I have another one. You show results in 1D for the Dirichlet-Neumann. So do you have results in 2 dimensions? Or?
Yes. In the thesis, there are also results in higher dimensions. Yes.
In your thesis? And the last results you show on Neumann and Dirichlet-Neumann of 2014?
Yes.
Do you have also...
They're also in higher dimensions, but only for strip decompositions, because otherwise we cannot evaluate these kernel estimates. They're too hard if you have cross points. We just don't know how to do it.
Okay. I remember my question. So for the you have a coarse solver and a fine solver in the Schwartz parallel. So you use also optimize Schwartz for the coarse solver?
The coarse solver is not a decomposed one in this case. So it's not, the coarse is like the parallel coarse, but it exchanges in the space like the waveform relaxation one. Okay. And so in the classical one I use Dirichlet, and in the optimized one I also use the optimized coarse.
For the coarse and
yes.
Okay. Okay, so thank you very much. And you have the coffee break now.
So welcome back to the third lecture of these time parallel methods. The third track is space-time multigrid methods. And on this same transparency, it's the blue methods. So you can also see these are all iterative methods, starting by Haag-Busch, Lubich-Ostermann, Horton van der Walle, Emmett Minion, and then also contribution from me and a collaborator. These are methods which are iterative in nature, and they solve the entire space-time problem at once by iteration. The first method in that class was proposed by Haag-Busch. Haag-Busch did not get so much credit so far in this CEMRACS school. Haag-Busch was a pioneer in multigrid methods, and he was very different from Aki Brandt. So Aki Brandt had many, many good ideas. He sort of knew how to make algorithms work, multigrid algorithms, whereas Haag-Busch knew how to prove that multigrid algorithms work. So they're very complementary. There were interesting discussions, endless discussions about who was right, who had the right approach. So I think Haag-Busch should get a lot of credit what he did for multigrid methods. And he's the first to propose such a multigrid method for a space-time problem. He called it parabolic multigrid method. So let's take the model problem that he used. It's a parabolic PD, so we have ut plus LH u equals f. LH is a discretized Laplacian. Ut is a time derivative. And discretized this problem with backward Euler in time. Now Haag-Busch uses a bit strange notation. He uses continuous time variables here, but you can see what it means. This is really a backward Euler step. It's u at t minus u at t minus delta t divided by delta t, plus the discretized Laplacian times u at t, so this is implicit, equals f. And then he says the conventional approach to solve star this problem, time step by time step, is time step by time step. ut is computed from ut minus delta t, then ut plus delta t from ut, etc. exactly like I've shown you at the beginning, one step after the other. The following process will be different. Assume that ut is already computed or given as an initial state. Simultaneously, we shall solve for u at t plus delta t, u at t plus 2 delta t, up to u at t plus k delta t in one step of the algorithm. So you see, it's the whole space-time problem, which is sort of solved by iteration here. So how does this method work, this parabolic multigrid method? It works as follows. I define the matrix A to be the term that comes from the time step plus the discrete Laplacian. And then at each step, one has to solve an equation A times ut equals the term from the previous time step plus the right-hand side. Now, for this matrix problem, I can consider a Gauss-Seidel iteration or Gauss-Seidel smoother. If I want to do this, I have to partition the matrix A into a lower triangular, diagonal, and upper triangular matrix. And then I get a new Gauss-Seidel iteration step by solving the lower triangular part from the upper triangular part from the old iteration and the part which is on the right-hand side in the problem. So this is just the Gauss-Seidel iteration that you would run at each time step to solve this linear system. Now, Hackbusch says, let's use such a process as a smoother as follows. There is an outer loop here which goes from t over all time steps up to k, t plus k delta t. But then instead of solving each time step, we just do new Gauss-Seidel iterations. So you see, this process is not solving time step by time step, but it solves approximately time step by time step. It does, for example, 2 Gauss-Seidel iterations, then 2 Gauss-Seidel iterations on the next, 2 Gauss-Seidel on the next, and so on. So this is not solving the problem, but it's approximately solving the problem, and it does this over many time steps. So this is what Hackbusch uses as a smoother for his multigrid method. It's a sequential Gauss-Seidel over several time steps. And then he gets the following results. If you use this as a smoother in a multigrid method, and if you only coarsen in space, then you get the typical multigrid performance for the Laplacian. So it's the good contraction rate independent of the mesh size. Accuracy increasing by a factor 10 at each iteration. So if you do this type of refinement, no coarsening in time, only coarsening in space, this method is good. If you also coarsen in time, it does not work. Sometimes you can get it to converge, but sometimes it even diverges. So this is the first multigrid method in space-time for parabolic problems, but it only works if you coarsen in space. In time, there's nothing you can do. It's just not working. Then there's a second important contribution by Lubich and Ostermann, multigrid dynamic iteration for parabolic problems. We studied a method which is obtained when a multigrid method in space is first applied directly to a parabolic initial boundary value problem, and discretization in time is done only afterward. So they don't even discretize in time now. They remain continuous in time. How can one explain this algorithm? I thought of explaining it as follows. We have the same parabolic problem that Hackbusch had. Here is a discretized Laplacian. There is a time derivative. Now, to explain the algorithm, I will do a Laplace transform. That's not what you do to run the algorithm, but to explain what it is. So I do a Laplace transform in time. We've seen Fourier transforms this morning. Fourier transforms transform derivatives into multiplications by the Fourier variable. That's the same with Laplace transforms. This time derivative becomes a multiplication by S, which is the Laplace variable. And then I write this problem as a linear problem for each value of S. I have an infinite number of values of S. So I just consider this now as a linear problem which depends on a parameter S. Now for this linear problem, the multigrid algorithm is well defined. If I fix S, I can just apply multigrid to this problem. So I apply multigrid to this linear problem, I fix S. So I split to get a smoother, I split into L plus D plus U. Now D, because this parameter is important, contains S from here. I start with some initial guess. Then I iterate this multigrid method. I smooth with Gauss-Seidel for a fixed S. This is just a Gauss-Seidel smoother. Then I calculate the residual. Like in every multigrid method, I calculate the residual. I restrict the residual to a coarse grid. I solve on the coarse grid. I prolongate to the fine grid. I add this to the correction. And maybe I do again a few smoothing steps here with Gauss-Seidel. This is a classical multigrid method applied to this problem if I fix S. So no thinking involved. It's just a classical multigrid method. Now we try to reinterpret what that means if I do a back transform of Laplace, because that gives an algorithm now. So what does that mean? The smoother, this Gauss-Seidel smoother that I used has an S on the left, and an L and the D on the left, and on the right it has a U. So if I do a back transform, the multiplication by S is becoming a time derivative again. So if you look at this iteration here, you see this is a waveform relaxation iteration. It takes a previous approximate iterate at step j minus 1, and it calculates the solution of an ODE with a lower triangular matrix. So this smoother that they defined in Laplace transform, if you look at it in the time domain, it's a waveform relaxation iteration. So this method uses as a smoother waveform relaxation. And then the coarse grid correction, if I do the back transform, so I back transform from S to T, you just get a coarse parabolic problem. Time is continuous. It's on a coarse spatial grid. So this method that they invented, it's a multigrid waveform relaxation method that uses multigrid as a smoother and the rest standard components. So in this method, you cannot coarsen in time because time is continuous. There's no concept of coarsening in time. So they get very good results. They get very good smoothing for Gauss-Seidel, even better smoothing for Jacobi waveform relaxation. And you get similar results if you discretize this algorithm in time, provided you don't coarsen in time. Never coarsen in time, otherwise this method is not working. Very nice example here on several time windows with a moving front with locally adaptive time stepping, which is solved with this multigrid waveform relaxation algorithm. But again, same problem. This is not really a full multigrid method because you cannot coarsen in time. If you coarsen in time, this is not defined. Whereas in Hackbusch, if you coarsen in time, it's not working. So the basic algorithm like it is for multigrid will not work in space-time. Now there was a substantial contribution by Horton and Van de Walle in 1995. And they say in standard time-stepping techniques, multigrid can be used as an iterative solver for the elliptic equation arising at each discrete time step. By contrast, the method presented in this paper treats the whole of the space-time problem simultaneously. So they also want to use multigrid in space-time, and they really want to coarsen both in space and time. They want a method that works like for the Laplace equation. So they write the whole space-time problem. So this would be the first time step. Then this would be the second time step, the third time step, up to the nth time step. Each of these matrices would contain a Laplacian to invert. So this is a huge matrix. It has all the unknowns in space times all the unknowns in time. And they say, we just want to solve this whole space-time problem by applying multi-grid, but really systematically, coarsen in space, coarsen in time. Now, there's an interesting quote I should have put here in the book by Gil Strang on finite element methods. They say that solutions of such evolution problems, if you considered them in space-time, would just not be tractable. It's too big. But in the meantime, you have so big computers that you can envisage to put such a big matrix. It's a space-time matrix, you just want to solve the whole thing. So what do? They first study numerically why time coarsening is not working. And there's a very interesting graph here. So they brute force apply a V-cycle to this space-time problem. Brute force. They use a smoothing, which is a Gauss-Seidel red-black pre- and post-smoothing. They do standard coarsening both in space and time with a factor 2, even though they know it's going to blow up, it's not going to work. And they measure how much the algorithm manages to contract. And there is a very important parameter, this is this lambda here. Lambda is the ratio of the time step and the space step squared. That's a parameter that appears in this algorithm. And they plot for different values of the log of this parameter. So at 0 here, this parameter is 1. How much this V cycle with 6 levels contracts. And you see, if delta t divided by delta x squared on the fine grid is about 1, the method converges. The contraction factor is 0.4. It's not as good as in space. In space, you want to have 0.1 for Laplace's equation. But it's working. And if you're a little bit above, it's working as well. If you're a little bit below, it's working as well. But now look what happens if you do coarsening with the same factor. If you coarsen this by a factor 2, this means this is coarsened by a factor 4 because there is a square. So lambda is going to move into one direction or into the other direction. So as soon as you start coarsening uniformly, even if you were in the good range in your multi-grid hierarchy, at some point you're going to arrive here or here. And here you see the algorithm is not working at all. At least on this side it's still contracting, but with 0.095. It's bloody slow, slower than a smoother alone. And here it's actually diverging. That's what Hack-Bush said as well. So the rho which is plotted here is just a 2-norm measurement of the contraction of this method. So if the lambda parameter on the fine grid is close to 1, then the hierarchy works. But if in the hierarchy somewhere this parameter is going away, the method will not work anymore. And even in the good range, it's not as good as spatial multigrid. So what can one do? There are key new ideas in this paper by Van der Waal and Horten. The first one is you do adaptive semi-coarsening in space and time. So you try to coarsen by a factor of 2, but as soon as your lambda is getting out of the range where it's working, you don't coarsen in time anymore. Or if you're on the other end, you don't coarsen in space anymore. You navigate so your lambda is always in the middle, because there you know you have contraction. So it's an adaptive coarsening, depending on which coarsening you can do and which you should not do. And then there's a second very important ingredient. It's the time prolongation and restriction operators. They define them in a causal way. They always take data from earlier in time, and they always propagate data later in time. And here you see from their 2-grid analysis the performance of what happens. That's now just 2-grid. Depending on the lambda factor, if you do full coarsening in space-time, so this would be the dotted line, and you see this analysis gives a very similar dotted line as what they measured in the 6 V cycle. It works around here. Here it does not work, and here it does not work. And then you see 2 more lines, the space coarsening line, which is a solid line. If you're in this area, you can do space coarsening in the 2-grid method. It will still converge extremely fast. But the more you do space coarsening, the more you move along this curve. And here you should not do space coarsening anymore because it's not working. Here you have to stop doing space coarsening. And with the time coarsening, it's the other way around. Here, if you do time coarsening, you get a very, very good performance. But if you do more time coarsening here, it's going to stop working. So with this Fourier analysis, you can navigate exactly the algorithm to be in a range where it's working in space-time. And that's what they do. And that's the performance they get. So on the left, it's the performance of a V-cycle, contraction of a V-cycle. And there are 3 curves. They're hard to distinguish. It's for different resolutions. Very fine resolution, less fine, even coarser, even coarser. And you can see the V-cycle is not completely robust. The finer you make the grid, the slower it gets, but it's still a very good algorithm. It contracts at a factor of about 0.2, space-time multigrid. If you use an F cycle, that's a full multigrid cycle that starts on the coarsest level and then just works its way up, then it seems to be robust. They do numerical results for 1D, 2D, 3D heat equations, and that's the first fully functioning space-time multigrid algorithm. It's a very good algorithm. It's very competitive. Then there was a different school, the Minion school. We had proof that the parareal algorithm is also a space-time multigrid algorithm with Stefan, but with very aggressive coarsening. And then Minion, he worked on a variant of parareal which is based on spectral deferred correction methods. Now, who knows what a spectral deferred correction method is? It's something which might be more known than Stefanson's method, but still it's not something that's in everybody's bag. So I'll first explain what a spectral deferred correction method is. It's an interesting method. It's good to know what it is. It's not complicated to understand. So what's a deferred correction method? It's also called difference correction or defect correction. I'm really trying to find out if there is a difference between those. There is none. This is all used interchangeably for the same type of method. So suppose you want to solve the ODE u prime equals f of u with some initial condition u0, and you just use Euler to do it, first approximation. So I calculate um tilde using Euler steps, forward Euler, for example. Then I interpolate the solution between these discrete points. Now I have a continuous approximate solution of the trajectory. Then the error, which is also a function in time, is the difference between the exact solution and my interpolated Euler solution. And now we can see what kind of equation this error satisfies. I take a time derivative here, a time derivative of the error. This gives me a time derivative of the exact solution and a time derivative of my interpolated solution. For the exact solution, I know this is f of u because the ODE is satisfied by the exact solution. For this solution here, there's not much I can do. It's just the derivative of my approximation that I interpolated. And then because I don't know what u is, I replace u from this equation here by the error plus u tilde. And now you see I have an equation for the error. E prime equals f of e plus u tilde. U tilde I know. It's my interpolated previous approximation. And the derivative of the interpolated approximation. The initial condition is 0, because initially I don't have any error. I know the initial condition. And now the crazy idea is you just solve this again with forward Euler. Then you get an approximation to the error. What can you possibly gain with this? There is an amazing result. It's going back to Skeel. Leslie Fox had already a late result. Victor Pereira had a result. There's also the Austrian school that had a result. The new approximation, if you solve this again with Euler and add it as a correction, is second order. And if you do it again, it's third order. Now you remember the parareal algorithm. Also every iteration gives you one order more. That's sort of very similar behavior. That's called difference or defect or deferred correction. You only pay Euler steps, but you do it several times, and you get order 2, order 3, order 4, order 5. Now, the way I presented it here, it's not really working, because you have to do interpolation, And then you have to do derivatives of this interpolation. Now, interpolation polynomials tend to oscillate towards the boundary. You take derivatives of these oscillations. So this is not a practical algorithm. But Dodd, Greengard, and Rocklin in 2000 found a way to rewrite this method to make it into a usable algorithm. And that's called the spectral integral deferred correction. The idea is to get rid of the differentiations by writing the ODE as an integral, like in the Picard iteration. So instead of looking at the ODE, we look now at this integral formulation. And assume I have again a forward Euler approximation that I interpolated. Then I can put this U tilde into the integral form and calculate what the residual is. Residual means I put this U tilde into this equation and look at what the mismatch is. The mismatch is the right-hand side evaluated at U tilde minus U tilde from the left. That's the residual. Now the error is again the difference between the exact solution and between my interpolated Euler solution. I assume that I start with the correct initial value. So this U0 there is also the U tilde 0. And then I can write on the left UT. UT is exactly this quantity. And on the right, I just put the U tilde. And again, the U I replace by U tilde plus E. Now I have an integral equation for E, for the error. This is an integral equation for E. I can solve for E. I have to evaluate this integral equation. And in this form, you recognize that the residual appears, almost. It almost appears. You see, the residual had a U0 tilde, which is here. The residual had a minus U tilde, which appears here. But in the middle, it had an F of U tilde. And here we have an F of U tilde plus E. So not quite. So I have to add and subtract an F of U tilde integrated. Then I get the residual, and I have to sort of subtract it again. So the error satisfies an integral equation with the residual and the error again under the integral. Now here is just a copy of this formula. If I take a derivative of this formula now, I get a differential equation for E. And if I solve this equation with forward Euler, if I want to solve this equation with forward Euler, then I need to approximate this R tilde, but this I can calculate from the residual with an accurate quadrature rule. And so here is the advancement of the error with the R from the quadrature rule. And it turns out that this procedure is numerically stable. This gives also deferred correction, but in a numerically sound way. And you have the same result here. If you start with Euler order 1, one iteration gives order 2, one iteration gives order 3, one iteration gives order 4. So that's spectral deferred integral correction. So how do you use this in practice? You use this if you don't want to implement the Runge-Kutta method. You just don't want to do a Runge-Kutta method of order 4. Then you use your Euler method. You get as an initial guess the U0, which are the Euler steps. And then you do on this vector, so that's a vector over a whole time window with many Euler steps. You do one iteration of spectral deferred, integral deferred correction. I write this as F here. Then you get a new approximation. You do it again, and each time you do this, the order increases. And this only stops when you reach the accuracy of the quadrature rule you used for the integral. If the integral had a quadrature rule of order 8, you cannot go beyond 8. After 8 iterations, if you do the 9th one, it's not going to get better. So how is this used? If you want to do time stepping instead of a Runge-Kutta method, you just partition the time interval into time windows. And on each time window, you use a certain number of Euler steps. And then you iterate this spectral deferred correction method as many times as you want until you have the order you reach, and then this time window is finished. And then you go to the next time window, you do Euler again, you iterate spectral until you have the order you want. So it's a process that works like this. So here you have time. You write time slices, ti plus 1. You do an Euler integration over several steps over this first time slice. Then you do spectral deferred correction iterations until you have order 4. And then you start with the value you have here. You do again Euler steps. Then you do the spectral deferred correction until you have the order. Then you do again Euler. Then you do spectral deferred correction. You do again Euler. You see, this is a time marching method like any other, except instead of having a Runge Kutta time step, you have Euler and spectral deferred correction to improve. It's a time stepping method. Now, what was the observation of Minion? Now you can try to see what changes in this algorithm. Something is going to change, something very small. Did anybody see what changed? Can you see? It's this index here. So what did Minion do? He said, suppose I have my first Euler step here. Then I have an approximation of the solution here. This is not a good approximation. It's first order. But who cares? Let's continue here with Euler. At the same time when I do the first spectral deferred correction here. So the initial guess is wrong now for the second interval. It's not because I should have first converged to fourth order here. But who cares? I just do one. And then in the next step, now I have here, so I do an Euler here. I take the value I get here from the first spectral deferred correction. I do 1. And here I do the second. So you see, this is sort of a pipelining thing. And I tried to prove, he has no proof that this actually gives spectral accuracy. I tried to prove I think it can do it, but I didn't do it very cleanly. So even if you don't wait for this guy to finish, this guy is still spectrally convergent here, because eventually it has the good initial guess. It's just at the beginning that the initial value is not quite the correct one. And then he said, now let's use this method as the fine propagator in parallel. You remember the parallel algorithm had a fine propagator f, which I said has to be expensive because you can do it in parallel. Now he says, forget about expensive, I don't want an expensive one. So in the first parallel iteration, I only use an Euler, a very bad approximation. But in the next iteration, I'm going to get a second order approximation from that first one. And even though the jumps that will be corrected by parallel even make this more incorrect, and there is no proof, it still sort of works. That was the first idea of Minion in 2010. But then they said, just forget about this. Just use this procedure as a smoother and build a full approximation multi-grid method for a nonlinear evolution problem. And that's an algorithm they call PFAST. Now, this name has a really funny story. You can see PFAST, P-F-A-S-S-T. This is Parallel Full Approximation Scheme in Space-Time. Now, you know, in the US, this would be pronounced FAST. And FAST is a very nice name for a method, because it means it's fast. So when he gave his talk at the workshop in Lugano, I told him, no, this is called PFAST in Germany, because we pronounce the P. And then first he was annoyed, and now he pronounces it everywhere like PFAST. So now it's known as PFAST, not as fast. It's a good method. It has been used successfully for many applications. It does consistently the course correction and the full approximation scheme, so it does it really like you should do in multi-grid. No convergence analysis, nobody knows why this works, or because we cannot even prove that it gives the right in the parallel setting, the right correction. But it's been applied to large-scale problems. It's working. And now I would like to explain the last method. That's a contribution that's coming from me and Martin Neumüller. I went to Graz a few years ago and gave a talk there, and Martin Niemöller was working on space-time methods. And he had sort of a space-time formulation, but no good solver. And then we looked at how one could do a multigrid solver from scratch that works well on such a system, without having to have special prolongations restrictions. And what we did is the following. We take the full space-time problem here, and the main new idea is we don't use a Jacobi or a Gauss-Seidel smoother, we use a block Jacobi smoother, which means we invert these blocks that contain Laplacians in each smoothing step. And then we do space-time coarsening. And we can prove for a heat equation that in the Jacobi smoother, which uses blocks, the relaxation parameter half is optimal. This is not like in the space multigrid method, there it's 2/3. Here you need to use a half. We can prove that you always get good smoothing in time, so you can always coarsen in time. You can do semi-coarsening in the time direction is always possible. We also have a criterion that says if delta t over delta h squared, delta x squared, is bigger than c, then we can also do space, so we can do full space time smoothing. And what we do is we don't invert these diagonal blocks. We just apply again a V cycle, but now in space. So this is a full space-time multigrid method. We have complete analysis. The paper just appeared. And this algorithm scales amazingly well on large-scale architectures. It's by far the best parallel solver I know for the heat equation in space-time at the moment. So here is experiments that Martin Niemöller did. These were in the Vienna cluster. He later did in Lugano. He did also on the large machines in the US. Here are two scaling experiments. You learned what weak and strong scaling is this morning. Weak scaling here is I increase the number of cores, and I increase the size of the problem. Iteration number of this space-time multigrid method is constant, and solution time is constant. You can scale as much as you want. Here there's 122 million unknowns, so the least ones are in the billions, the latest results. And it also has very good strong scaling. Frederick explained strong scaling at some point will stop, because you don't have anything to solve anymore. But you can see in this, for this size of a problem, if we increase the number of cores like this, iteration numbers are constant, and solution times are halved. Even here, they're still halved. This is by far the best I've ever seen. This is as good as multigrid gets for a Laplace problem on a large-scale architecture. It's really an outstanding algorithm. Very, very good. So this is a summary about space-time multigrid methods, what you've seen. And we can have, when do I stop? At 5? Yeah, we can have like 15 minutes break now, I think. It's worthwhile. Thank you. So I will start the last, fourth lecture about direct time parallel methods. This is the same graph that we've seen 4 times now. The direct time parallel methods are more like small-scale methods. There are some that are getting large scale as well. These are the black methods on this transparency. You see there are many. And these are maybe the most improbable methods, because all the methods we've seen so far, you've seen that we used, as a trick, we used iterations to get the solution over the whole space-time. Now, these methods do not iterate. They use many processors, and they somehow manage to do this in parallel. The first method is by Miranker and Liniger, almost as old as Nivergeld, 1967. And here is the idea of this method. They first also described that there is no parallelism in time integration. And they say the computation front is just too narrow. You compute like this, and so there is no way to do parallel computing because you're just advancing like this. And then they say, let us consider how we might widen the computation front. So they somehow want to change this front into a front where suddenly several things can be done at once. And here is the concrete example from their paper. So they take y prime equals f of xy, And they consider predictor-corrector formulas. Predictor-corrector formulas are formulas that have 2 steps. So here is an example. You first predict the new value, yp, at step n plus 1, from the yn corrected value, and some combination of other corrected values earlier. So you see, you need ync and yn minus 1c. So here is a cartoon of this step. If you know y at n minus 1 and y at n, in this predictor step, you calculate the value up there. You see there are 2 arrows. If you take these 2 values, you can predict the step up there. Now, once you know the predicted step, there is a second formula, which is called corrector. It uses the corrected value at step n. And it uses the predicted value at step n plus 1, and again the corrected value at step n. That's the second set of 2 arrows. You use the predicted one from above and the corrected one to get n plus 1. Now you see, this is completely sequential. You first have to do this predictor step, because this value is needed to do the corrector step. Now they say maybe there are methods where this is not like so. So here is another predictor-corrector method. And here what you use is you use the corrected value from n minus 1, and you use the predicted value from step n to get the predicted value from step n plus 1. So in the cartoon, you can see here, you use the corrected value from n minus 1, and you use the predicted value to do the new prediction. And for the correction, you use the corrected value at step n minus 1, the predicted value from step n, and again the corrected from step n minus 1. So if you look at the arrows here, you can do the prediction at the same time as you do the correction, because the prediction you do 1 step ahead. So suddenly in this method, these 2 steps can be done in parallel. You can use 2 cores. So see, this is a direct method. There is no iteration. You just advance with 2 cores, and you get the same order as with this method. With this method, you can only advance with 1 core. And they define in this paper such type of methods where it can use 2 S-cores. And there is a complete stability and convergence analysis. They're not quite as good as these methods, but they're parallel. So if you have a 4-core or an 8-core machine, it's worthwhile to take this integration method, and you just integrate through like this. And it goes in parallel. That's the first direct method, no iteration. Then there were block implicit methods by Champagne and Watts. Maybe I don't explain those. It's a variant of the previous method, just in a more general formulation. But in the very well-known book by Heyrer, Norset, and Wanner from 1992, these are Heyrer and Wanner are famous professors from Geneva University. They're numerical analysts, and they are the reason why I wanted to go to Geneva. I had seen their book on numerical ODEs, and it's the best I have ever read on numerical ODEs. And so I knew their name, I knew their work, and then I was at the airport in Australia going to a conference. It's a long time ago. And then I heard Austrian in the line before ahead of me. Somebody was speaking Austrian, and I thought, wow, I could speak German to them. Because, you know, so far away from Europe. So I said, hi, where are you going in German? And then he turned around and said, we're going to a conference in, and I said, I go as well to a conference. And then he said, my name is Ernst Heyrer. And I almost fell over. Because I knew what this guy is capable of. And you might have heard 2 years ago, his son won the Fields Medal. So this is really like, this is mathematics, which is from a different planet. This is just outstanding. So this is a very famous book. It's the best you can read on numerical ordinary differential equations. There is a 2nd volume for stiff problems. There is a 3rd volume for geometric integration. If you need to learn about numerical ODEs, there's nothing else that gets even close to this. So when I started working on these time parallel methods, I also talked to Ernst, and he said, you should look in our book. We also have methods that are time parallel. So I looked. And I found a few quotes that are really funny. They have quotes in their books. So the first one is, it seems that explicit Runge-Kutta methods are not facilitated much by parallelism at the method level. That's by Arje Zerles and Siver Norset in 1990. And then there is a glitch that happened to Kevin Burridge, that's the guy who wrote the summary book. In a talk, he said paralyzing ODEs instead of parallelizing ODEs. Paralyzing means you're paralyzed afterwards, you're not moving anymore. So what are these methods that are in the book? It's parallel Runge-Kutta methods. I didn't know that that exists. So here is a Runge-Kutta butcher tableau. You must have seen butcher tableaus. This is the way you can note Runge-Kutta methods. So you have the A coefficients in this block, which tell you how each stage advances of the Runge-Kutta method. You have the C coefficients in this block, which you don't need, only if you evaluate functions. And you have the beta coefficients here, which tell you how you advance to the next step. So there's a way how to describe Runge-Kutta methods. An explicit Runge-Kutta method is lower triangular. And what you do is then you evaluate the first stage, the second stage, the third stage, the fourth stage, and once you have the fourth stage, you take a linear combination. Now, how can you make this parallel? You can make this parallel if the stage evaluations are independent of one another. And in this butcher table, you see the second stage and the third stage, they are independent of one another. So you can do those in parallel. And so here is a graph that shows you the first stage you have to do, then the second and the third stage you can do independently, and then the fourth stage again needs all three previous stages. So this is a small parallelism within a Runge-Kutta method that has a certain shape of a butcher tableau. And there's a very nice theorem by Jackson and Norset from '86 that says if you have an explicit Runge-Kutta method, which means you have a lower triangular matrix, and if you have sigma sequential stages, here you would have 1, 2, 3 sequential stages, even though there are 4 stages, but 2 you can do in parallel. So if you have sigma sequential stages, then there is an order barrier. You cannot get a higher order than sigma. So then the search for p-optimal, parallel optimal methods started. What are the methods that are Runge-Kutta methods that are optimal in that sense, that are exactly at this barrier? And there are families which are known. There are parallel iterated Runge-Kutta methods, and there are also the GBS extrapolation methods that are p-optimal. So these are Runge-Kutta methods that sort of run like this method that's deep, that widens the computation front. But it's a classical Runge-Kutta method you can just run. There's nothing to think about. So these are good methods, but at small scale parallelism. Again, multi-core, not more. Then there was a very clever method I saw by Christley, MacDonald, and Ong. It's based on spectral integral deferred correction. And that's why it was important to explain this in detail in the previous lecture. So we discussed a class of integral defect correction methods which is easily adapted to create parallel time integrators for multi-core architectures. So you see, again, it's small-scale parallelism, 4-core, 8-core, not more. So here is a cartoon of how we've seen the spectral deferred correction works usually. You take, let's say, 3 Euler steps, and then you do the spectral deferred correction exactly like I was drawing it here. Then you go to the next, you do the spectral deferred correction, you go to the next, and so on. That's the classical way to use this. Now, the new idea is called revisionist integral deferred correction, or RIDIC. RIDIC. You might hear about this later in your career. This is something that will go for multi-core. It's a very elegant thing to do. What they do is they say, forget about this organization of the calculation in blocks. Don't do blocks like this. Finish the block, this, finish the block, this, finish the block. Just have a first processor going with Euler. So this guy goes. Now, as soon as there are enough points available to do a spectral deferred correction calculation, just do one. So there is a second processor. As soon as we have 4 nodes, he would just advance this one by 1. And at the same time, because here we have 4 nodes, this one can produce a new one. And here we have 4 nodes, this one can produce a new one. So you see, it's a pipeline form of this algorithm, but it's really a different way of calculating it. You base the spectral deferred correction on different nodes. So with this, they can calculate with an octa-core in the same wall clock time a solution of accuracy 8 at the cost of Euler propagation. That's really amazing. So you have an octa-core. There is a small startup cost. Once the pipeline is full, you just go. It's a very elegant algorithm, very easy to use. But it's a very, very good invention. Then there is another idea, which is also a direct time parallel method, which goes back to cyclic reduction. It was an invention by Worley, and it was made to improve waveform relaxation. You remember waveform relaxation was an algorithm from the electrical engineering community. I've shown you Jacobi and Gauss-Seidel, waveform relaxation. And in each iteration, you have to solve a scalar ODE if you do Jacobi or Gauss-Seidel waveform relaxation. Now, the scalar ODE you still solve sequentially, and that's what Worley says here. The waveform relaxation multigrid algorithm is normally implemented in a fashion that is still intrinsically sequential in the time direction. Because at each waveform relaxation iteration, you solve over the whole time window, but you just solve by forward marching. So his idea is really clever. I learned about this because Stefan van der Walle said this idea is missing in my review paper. So here, suppose we have an Euler forward marching. It's a lower bidiagonal matrix. I have 4 unknowns I want to calculate. I have a right-hand side. If I do one step of cyclic reduction, what does that mean? That means I eliminate every other variable. I eliminate x1 and I eliminate x3. So x1 is very easy to eliminate. I can calculate what x1 is. I just put it on the right-hand side. And x3 is also easy to eliminate, provided I can eliminate the variable from here with a Schur complement. So you see, going from here by here, the number of unknowns is cut in half, and I still have a bidiagonal matrix. And if I had many more unknowns, I can do this many times. If I have 8 unknowns, I get down to 4 unknowns, still bidiagonal, down to 2 unknowns, still bidiagonal. I can build the whole tree. That's cyclic reduction. Now, in a serial context, that's not of interest. In a serial context, if I just do forward substitution, this costs 3n operations. And cyclic reduction, by doing this reduction, costs 7n. But if I have many processors, then the tree that starts to form, I can solve that tree using many processors. So the parallel complexity is a log in n of cyclic reduction. So here you go down from n to log n. And if I do this for a system of ODEs in waveform relaxation, so this is a system of ODEs. To do waveform relaxation, I partition again the matrix into lower diagonal and upper triangular matrices. I do here a Jacobi waveform relaxation, so at each step I have to solve scalar ODEs. Each scalar ODE is exactly this lower bidiagonal matrix that I have to solve. And if one does this with cyclic reduction, then you get to a parallel complexity. That's a theorem by Worley, which says that it's log squared number of spatial nodes times log to the gamma number of time nodes, where gamma is a half times the rounded up number of levels you get in this cyclic reduction hierarchy. And this is very much comparable to the space Laplace multigrid complexity. There have been papers, important papers by Stefan, that followed up on this. This gives a theoretical complexity which is optimal for a parallel complexity of this type of algorithm. It's a clever idea. Again, a different idea by Sheen, Sloan, and Tomé, also non-iterative. If you want to solve this ODE, system of ODEs, suppose you really do a Laplace transform. So this only works for linear systems. If you do Laplace transform numerically, you just do it, then you get this system to solve. So this to solve means you have to invert this matrix, which depends on the Laplace parameter. And then you have to do the inverse transform, which means you have to calculate this contour integral for the u hat s, which you calculate from this inverse. That doesn't seem very promising. But if you do quadrature on this, this means you only need to know this quantity for a few points s, let's say 10. That means you only need to know 10 u hat for 10 values of s, which means you have to do 10 solves here. These solves are all in parallel. It's completely parallel. And then you get an approximation of your solution in time. So you see, this is a method that produces the whole trajectory by solving a few times the system here for the quadrature nodes in Laplace. This seems to be the best method when it's applicable for linear system. There's going to be another one that is competing with this, which is different, but this has had a lot of success as a method. Now, this is probably the weirdest method. This is really a bizarre method. It's also a direct method. It was invented by Yvon Madet and Rencontres, also an autocrates like the parallel algorithm. Pour briser la nature intrinsèquement séquentielle de cette résolution, on utilise l'algorithme du produit tensoriel rapide. So some of the tensor product will only appear very late in my explanation. What's the idea of this method? So I discretize ut equals lu. L is again a Laplacian, but at the beginning, let's just think of a number. L is for here just a number. And I do backward Euler. Then I get this lower bidiagonal matrix. Bu, lower bidiagonal matrix, times all the steps, time steps, equals the right-hand side. So I have to solve the system Bu equals F. It's lower bidiagonal, so you would forward substitute if you were in the right of your mind, but here we want to do it parallel. So suppose you can diagonalize B. Now, before I continue, is there any chance I can diagonalize this matrix? Suppose all delta t are the same. Then the diagonal elements are all the same. It's a lower bidiagonal matrix. This is a Jordan block. You cannot diagonalize a Jordan block. A Jordan block is the matrix that you cannot diagonalize. It's impossible. All the eigenvalues are the same. There's no way to diagonalize this matrix if all the time steps are the same. That's why here the time steps are not the same. Because if you don't choose the same time step, then it's not quite a Jordan block. It almost tries to be a Jordan block, but it's not. So if the time steps are not the same, then it is possible to diagonalize. And if you diagonalize this matrix, then instead of solving Bu equals F, you have to solve SDS inverse U equals F. And that has 3 steps to do. First, you have to solve SG equals F to get G. Then you have to solve a diagonal matrix equals G. Now, a diagonal matrix is solved in parallel. Each element you can do in parallel. And then you have to do the inverse transform from this diagonalization to get your solution. Now, B, as I mentioned, is not diagonalizable if all the time steps are equal. So this method is not even defined if all the time steps are equal. Even if 2 time steps are the same, you cannot diagonalize it. So how should one choose delta Tj to get this into a usable method? So there are 2 things. The first thing we try to see is maybe it's interesting to have different time steps. Maybe you get more accuracy. And there's the first result that came out of this. This was a calculation at Onera, where we just calculated. So you just set up an optimality system, you differentiate, you look, and you find out for backward Euler, the truncation error is minimized if all time steps are the same. So the best error you only get if the time steps are the same. So if you make different time step, you're losing something. It's going to be not as good as having the same time steps. But to use this method, you have to take different time steps. So Yvon proposed to do a geometrically stretched grid. So you start with a time step, and the next one is a little bigger, and then the next one is a little bigger, so you stretch it a little bit, because then all the time steps will be different, so you can't diagonalize. But the result is a bit less good than if you had taken the same time steps. So then we thought to analyze how good a solution you can get with such a method. because now we have two competing requirements. We want to have the time steps almost the same, because this gives the lowest truncation error, but we want to have them different to make this diagonalization work. And so there are two results. A first result says, if I use a geometric mesh with a stretching epsilon, then the difference between what I get for the stretched mesh and the mesh that uses the same time steps, it's a constant times epsilon squared, where this is the stretching, plus smaller terms. And the constant we can calculate for this model problem. So we know the more we stretch, the worse the truncation error gets. So we don't want to stretch too much. Then there is the second requirement. I want to diagonalize this system. Now, if you diagonalize a matrix which is almost a Jordan block, you're going to have numerical problems. There's going to be round-off creeping in. And so we studied how much round-off is coming in this solution process. And we can show if we solve on a computer this bidiagonal matrix by diagonalization for a stretching epsilon, then the error that we will get from the solution process is again a constant. You see the machine precision comes in. It depends on the number of steps. It depends on the problem parameter, times 1 over epsilon to the n minus 1. So here we see very clearly the two competing requirements. This here says epsilon should be big to have a small error. The other one says epsilon should be small to have a small error. So you need to balance to get a method, and then you can see if this method is useful. So that's what we do here. The error between the exact solution and the numerically computed solution by diagonalization for a stretched grid epsilon, it's bounded by the normal truncation error without stretching, plus the error which is due to the fact that I did diagonalization, and the round-off error, which is because I had to numerically solve it. So we balance these two errors, and we get a formula for the best epsilon for this method. And we can calculate it. Here is the formula. So if you want to solve from 0 to capital T, if you have an ODE that has an A in it, if you do n processors, which means n steps, then the epsilon you should choose is this one. This is going to give you the best possible result. And because this formula is hard to interpret, I plotted the result. So here you have AT, it's homogeneous in AT. Here you have AT, that's a problem parameter. Here is the number of processors you will use. And so you see, for example, if you have AT equals 50, then if you want to use 15 processors, your epsilon should be 0.25. Do you still get a useful result with this? That's the best you can do with this algorithm, but maybe the solution is complete crap here. So that's why we calculated how big the error is if you do this choice. So you can look, this is a plot of how big the error, how much is added to the error that you would get without parallelization, without stretch grid, etc. So for this, if you do the best choice, 15, the error would be multiplied by about 7. Now, is that tolerable in your application? I don't know. Maybe that's too much. But if you only want to use 5 processors, you only add 1% error. So here, maybe you can tolerate it. Or if you want to do 10 processors, your error is doubling in this range. So maybe this is tolerable as well. So even though this method sounds completely crazy, this mathematical analysis shows that for a certain range, the range here, this is useful. Now, why is this parameter A important? It was a scalar ODE that I analyzed. But if I have a Laplacian, then the spectrum of the Laplacian is coming in here. Then I have many different A's. And you can see with 5, maybe 8 processors, I can get by with this method because this levels out here. But not many processors, not 20, 30, or 40. This is just an illustration of the accuracy of these estimates. Now, where did tensorization come in? Because the name had tensorization in it, of Lyons and Rencontres. if I really have a Laplacian, so here is now a Laplacian, I do backward Euler, then this method cannot be applied immediately because the time-stepping matrix B also contains Laplacians now. So I have to rewrite the system using Kronecker products. So there is the time-stepping matrix times Kroneckered with a spatial identity, and then there is the identity in time Kroneckered with the Laplacian. So this is the time-stepping matrix as before. And now I can do this diagonalization just on the time part in this Kronecker structure by doing an algorithm with 3 steps. And here in the middle, you get now as many Laplacians to solve as you did time steps. That's why it said tensorization in the title. So this can be used for systems provided they're linear. Here is an example. Now I'd like to explain the last algorithm. This is para-exp. This is also a clever invention of Stefan. This invention happened when we tried to use a parareal method for a wave equation. I did not mention this so far, but most of the algorithms you've seen, except for the Schwarz wave formalization methods, do not work for wave equations. They need dissipation. And so there was a variant of parareal that Farhad proposed that creates a subspace, a Krylov subspace. Stefan Güttel was a specialist in Krylov subspace methods. When he did a postdoc, I asked him to analyze this method, and he basically showed that the cost of using the Krylov subspace is way too expensive. It's not a useful method. But then he had a different idea, and here is this idea. This is a method that only works for linear problems. It works as well for heat equations as for wave equations. So here is an example, u prime equals au plus g. And it's a direct method. It has 2 steps to calculate. The first step is that you solve on a non-overlapping decomposition in time inhomogeneous problems. So you use the source G, but you start with a 0 initial guess. This you can all do in parallel. So you solve with a 0 initial guess, with the right-hand side source, all these red trajectories. No communication. This is just a solve. And then in the next step, you solve the blue problems. Now, the blue problems use the initial condition, u0, then what the red one calculated, and you solve over the long time interval, the blue problem. These can also all be done in parallel. And because this is a linear problem, the solution is just the sum. You just sum up, then you get the solution. Now, this immediately seems to have a catch. The blue problems integrate over long time intervals, you see. So how can you gain anything in this algorithm? If one blue processor has to integrate over the whole thing, he could just integrate the original problem. Now, the key idea here is that the blue problems can be solved much, much faster than the red problems. Homogeneous problems, these are homogeneous problems, the blue ones. They can be approximated very well as a matrix exponential in a rational Krylov space or in a Chebyshev approximation. So the blue problems, even though they propagate solutions over very long time intervals, they're much, much cheaper than the red problems. So this is an algorithm that allows you to solve wave equations in parallel. It has extremely good efficiency. For a wave equation, it's very hard to get efficiency at all. Here you see a table of many numbers. Here is the serial cost, and here is the parallel cost of the model problem above. You see it's a wave equation with wave speed alpha. It has a hat function that oscillates as a source. And we use different wave speeds here, different frequencies for the oscillation. And the sequential cost of just solving to a given accuracy, which is given here, is 10 to the minus 4, is given here. That's the sequential cost. And here you see the parallel cost to get to the same error level. And there are 2 columns. This one here is for the red problems. And it's the maximum time that any of these processors use to solve a red problem. And here is the time for the blue problems. And you see, even though the blue problem propagates over much, much longer time, because it's a rational Krylov method, it's very, very cheap. This cost does very, very little affect the main cost. And that's why you get very good efficiencies here. The same thing also works for a heat equation. Very similar performance. So this is really not dependent of the nature of the problem. It also works for advection diffusion. This is a typical benchmark problem. So to conclude, here are the direct space-time parallel methods I discussed. And I'm happy to take questions. Thank you.